Next, we'll look at an example of Hilbert's Grand Hotel. How can we accommodate a new guest arriving at the fully occupied Grand Hotel without removing any of the current guests? The Grand Hotel has a countably infinite number of rooms, all occupied by a guest. Since the number of rooms is countably infinite, we can sequence them indexed by our natural numbers. So we can call them room 1 or R1, R2, Rn. When a new guest arrives, all we're going to do is take whoever was in room 1, move them to room 2. Whoever was in room 2, move them to the next room, and so on as we go down the line, which means we'll add a new room at the end, which we can do because this is an infinite set. So we end up with the new list being R1, R2, Rn, Rn plus 1. Now, everybody who was existing already there as a guest has a room, and we have enough room to put the new guest in, and we put that new guest in room number 1. So this would be something that's not possible in a finite set, but since we have a countably infinite set, we can in fact do what looks like a paradox here, being able to add and accommodate a new guest in a hotel that has all of the rooms currently occupied. And this is the trick of being able to have countably infinite sets. Next, we'll look at an example to show the set of all integers is countable. In order to do this, we need to show that either we have a one-to-one correspondence with the set of natural numbers, or that we can index the set of integers as the set of natural numbers. So let's just take a look at that. The two sets that we're looking at and trying to compare, essentially we're saying the set of integers has the same cardinality as the set of natural numbers. So we're saying that, say, -3, -2, -1, 0, 1, 2, 3, ... is essentially the same as saying 1, 2, 3, ... And we're saying that those two have the same size. So is there a way that we can list all of the integers indexed as a term of natural numbers? So there are a variety of different ways to do this. We could do it just kind of setting it up as a table here, putting the natural numbers over on the left, put the integers over on the right, and list out our natural numbers. And then we can write the integers like this. We can start with 0, since 0 is smack dab in the middle of a mirror image between negatives and positives. And then we can alternate between writing the positives and then the negatives. So I write 0 goes with 1 of the natural numbers. 1 from the integers goes with 2 from the natural numbers. -1 from integers goes with 3 from the natural numbers, and then we'll start on 2. 2 from the integers goes with 4 of the natural numbers. -2 goes with 5 from the natural numbers, and we'll keep on going and fill this table out. So we go 3 and -3 and 4 and -4 and so on as we go on down through. And if I'm going to make this even, then I should associate that -4 with 9 from the natural numbers. And what we've done is created a one-to-one correspondence or a mapping of all the elements from the natural numbers to the integers. So in fact, we are able to count the integers. So this is a countably infinite set, just like the natural numbers is a countably infinite set. For the next example, we'll show that the set of positive rational numbers is countable. To do this, we need a sequence that can be indexed by natural numbers. Let's call those elements R1, R2, ... Rn ... And let's note that every positive rational number can be written as a quotient of P over Q of two positive integers. Let's arrange those positive rationals in an order with the denominator Q equals 1 in the first row, then Q equals 2 in the second row, and so on. The numerator will also start with a P equals 1 in the first column, and P equals 2 in the second, and so on. This will allow us to create a grid that contains all possible positive rational numbers. So I've drawn them out in a grid here, and what we're going to do is try to come up with some sort of a way to write these in a sequence that will allow us to write the sequence based on a relationship with the natural numbers. To do this, we'll list the sum of our P and Q. So we'll go P plus Q, and then we'll list what element from the rationals that is equal to. So for the first one, P plus Q is equal to 2. Okay, and that is going to correspond with this term right here. So this corresponds with the term 1 over 1. Next, for P plus Q, going down from here to here, we can get our P is equal to, P is equal to 1, and Q is equal to 2, so that is term number 3, and that is this term and this term, because the sum of each one of those is 3. And I'm just drawing these little arrows to give us a visual direction of where we're going with this. So term 1/2 and term 2 over 1, or simplified as just 2, is there. Next, we'll go from this term to this one. So we get P is 3 and Q is 1. That's the term where the sum is equal to 4. That gives us our term 3 over 1. When we look at the next term where the sum is 4, that is this term here, which is 2 over 2, and this term here, which is 1 over 3. Now, whenever we list these terms, what we're going to do is say we are not going to repeat any terms that are already listed. So that takes 2 over 2 out of the list. So that one is not going to be listed. The rest of them are unique, so they will be listed. From there, we go down to this term, which is the 1 over 4. So we have 1 plus 4 gives us our sum total of 5. And notice each one of these sum totals follows the pattern of going diagonal right up the line. And again, we'll want to look at these, make sure that those are all unique. List them out. We have 1 over 4. We have 2 over 3. We have 3 over 2. And we have 4 over 1. And each one of those is unique. From there, we would go to the next, which is 5 over 1. So we have 5 plus 1. Sum total is 6. And that will take us down this row, or this diagonal rather, here. And let us look at each one of these terms. 4 over 2, that term has already been taken. That was simplified out to 2, which was up here on our first row. Right, get the laser pointer, go right there. So that one's already been taken. 3 over 3, this term right here, well, that's the same as 1, so that's already been taken there. And 2 over 4 is 1/2. That was already taken right over here. So we don't circle those. And we'll keep on going, following this same pattern down to the next term and going up in the diagonal. And this would allow us to hit every single term in the positive rational numbers and list out those terms based on an index according to natural numbers. Therefore, these are countable. Let me go ahead and list out those remaining pieces from the sum is 6 column. Okay, and there we go. And that concludes this proof. We've shown that the positive rational numbers are indeed